So welcome. So this is our beginning of the third bit, which is on basically the same chapter as last time. It's the second half of it. Tends to be a long chapter. What we're going to do today is we're going to talk about families of graphs, but these graphs are related. I showed you those three graphs last time, and they were just straight line graphs, and we said, oh, if it's a position versus time graph, the slope is the velocity. If it's a velocity versus time graph, the slope is the acceleration. If it's an acceleration versus time graph, the slope is the jerk. And if it's a velocity versus time graph, the area under the graph is displacement. And if it's a acceleration versus time graph, the area under the graph, well, that's going to be your average velocity. It's like boom. Okay. Now we're going to look at families of those three graphs that live together, that actually one causes the other, which causes the other. And they're going to have very specific shapes. So we're going to look at families of graphs, and we're going to start off with constant acceleration because it's easier mathematically, and it's also important. Link, I hope you got this from fundamentals. Link force with acceleration. If you have a net force, you have a net acceleration. The bigger the net force, the bigger the acceleration for a given mass. So link forces with accelerations. When we get a constant force, we have a constant acceleration. So everything that's under the pull of gravity has the same acceleration. Well, that's not so clear. They have different weights, so why do they have the same acceleration? I got myself into a little bit of a hole here. If F equals ma, then A equals F over m. And as the force gets bigger, so the mass gets bigger because it's the mass that causes the force. So everything has the same acceleration, constant acceleration towards the Earth. Minus 10 meters per second squared. In some classes they say minus 9.8, but life's too short. Not minus 10 is close enough. Okay? So that's what, so it's a very relevant thing to say. Let's look at constant acceleration bits. And it's mathematically more accessible to us. Okay. We live, can we derive a family of kinematic equations? You bet we can. Can we derive a family of kinematic equations using calculus? You bet we can. Then can we use these kinematic equations to solve one-dimensional problems involving motion? And can we use these equations to solve that subset of problems where the acceleration is specifically 10 meters per second squared downwards because the thing's in a thing called free fall. So these are basically two types of similar problems, and we'll show that. So here's our three graphs. If basically I have a constant acceleration, then that means I add the same amount of change in velocity to the velocity each second. So if this is, say, positive 2 meters per second every second, then whatever I start off with, after 1 second, I'm going to be 2 higher, I'm going to be 2 higher, I'm going to be 2 higher, I'm going to be 2 higher. So a horizontal acceleration means it's constant, and that gives rise to a linear changing velocity. When you have constant acceleration, you have steadily changing velocity. And if it's a positive acceleration, you're going to have a positive sloped velocity. If you have a negative acceleration, if this is below this guy, if it's a negative acceleration, you're going to have a negative going velocity slope. Where does it start? It depends. It could start there. It could start at a higher velocity. It could start at a middle velocity. It could start at a lower velocity. It could start at a negative velocity. Where you start is another issue. How you change depends on that acceleration. And if I take, now I've gone and scribbled all over this, but if I take, but let's erase it a little, let's just clean it up a little bit. So if I now look at my velocity versus time graph, and I divide this up into equal time intervals, then you can see that each second I had that amount of displacement to my object's position, and each second I'm adding more displacement to my object's position. Each second the areas are getting actually bigger. So I add a little bit of displacement, I add more displacement, I add more displacement, and I add more displacement for each consecutive second. So the acceleration must be a constant horizontal line if it's constant acceleration. That causes some kind of linear sloped line. If the acceleration was 0, which is constant, it's just 0, then I'd get a horizontal line here. As I go higher, I get steeper slopes. Yeah? And whatever the slope is, I'll get a parabolic shape for that. And again, if it was a higher slope, I would get, that happening. If it was a more gentle slope, I would get that happening. Yeah? So those family go together. Okay. So, little question here. Which graphs, we can't do the clicker for this, but we can do it just by shouting out. Which graphs are produced in a constant acceleration journey? So this is acceleration versus time. So is this constant acceleration? No, it's not, clearly not. Now we have a velocity versus time, but this is a curvy kind of graph. Is that constant acceleration? No, it's got to be a straight line, hasn't it? This is displacement versus time. Is that constant acceleration? Yeah, that could be. Oops, that's a check. I meant to do a check mark. Acceleration versus time? Yeah, I think so. Velocity versus time? Yes. What can you tell me about the sign of the acceleration for this journey? It's going to be a negative because we get in a decreasing velocity or a more negative velocity. Rather than adding a positive velocity on every second, we're adding a negative velocity every second. Yeah. And then this one, trouble with curves, the reason why in lab is we always try and get rid of curves is because they all look the same in the end. So who knows what I actually drew, but schematically it's a parabolic curve. So yeah, cool. So let's do some derivation. So time was when science consisted of looking out your window, seeing something, looking for a pattern, then writing it down in a book, and that would make you a scientist. And it's really, that's what science is often about. And you see what's obvious and you codify what's obvious. You can still make a whole bunch of mistakes, but, you kind of see what you see and you codify it and you write it down, and that's an aspect of science. The kind of next level is you kind of build a model in your mind of what's going on, and then you try and predict and play with what's going to, if I do this, what happens to that? That model might, in your mind, be a visualization of a machine, or it might be an equation, or it might be whatever, yeah? And usually what happens is you get some revelation, you get an answer, and you go, oh, this means that, and you get some insight that you didn't have just by looking at the thing. You got some deeper insight. And that's when you're making scientific progress. And an awful lot of science is done like that. A lot of science, a lot of engineering is like that. In your life, you will make up equations. You'll have some gizmo that you designed for an instrument, and somebody's going to say, what happens if I turn this? And you'll figure out an equation, or you'll figure out a graph, and you say, when you turn this, if you double this, you're going to get a 10th there. If you triple this, you're going to get a 30th there, and you're going to make up some equation that links it. We all do it. It won't be a famous equation. It'll only work for your box. You won't be talked about 400 years later, but you'll do your bit. You'll be doing what the famous people did. And this is part of that. This is a noble tradition. In fact, what happens with some of the more modern stuff is, kind of take a complicated model, and then you do an awful lot of math in it, and you come up with answers. And it's not even like, unless you're really good at the math, you can't really see the math steps. And you believe the answer, no matter how crazy it seems, because you're confident about the math steps. And to some extent, that was Albert Einstein. At the time, people were looking for the ether that carried the light waves. The new light was a wave, so they're looking for the ether because all waves have a medium that they ride on. And if there's an ether and we're traveling through space, we must be traveling through the ether. And so it's like dropping pebbles on as your canoe drifts downstream. You can look at the speed by which the water ripples go out relative to your canoe, and you can tell which direction you're flowing relative to the stream. You can learn stuff. And they said, man, if we send light one way and another way, we can figure out which way we're going through the ether. And they could never find a difference. And they went crazy about that. It's just, we need a better experiment, we need a better experiment, we need a better experiment. And Einstein was kind of the one who basically said, there's no ether. Let's just work on the principle there's no ether. What do I have to change to get the answers I'm seeing when there's no ether? And he started off and he built a system, and the answers seem crazy. Time slows down, lengths contract, momentum increases. And he said that's true, basically. And the reason why he's so famous is because he said something which on the face of it just seems absolutely, it's drivel. Time slows down, oh come on, you know? And lengths, a ruler gets shorter because it's traveling down the road. This is nonsensical. So he said it, and people kind of like, this guy's an idiot. But then the experiments get done, and he's right. You don't get famous for saying, me too. You get famous for saying something that on the face of it seems outrageous, and it's right. If it's wrong, you're that wacky person who said something that's, and it's wrong. And then since then, I'd say an awful lot of cosmology is like that, where, and string theory, it's like, as an outsider, you can't really assess what's going on with something like that, because it's so specialized, and the axioms and the math and the like is a special field. That's a problem, because lay people can't really appreciate it. They can accept it or not accept it, but they can't really appreciate it. As a layperson, you can look at speeds, and you can look at displacements, and you can look at that. So science becomes less and less accessible. And math becomes more and more, the math begins to drive the science rather than the science driving the math. And that's just the way it is. And that's why you need two strings to your bow. You need to be a good visualizer, and you need to be a good mathematician as well. So this is part of the process. And so what do? We basically say, look, we know this relationship. Let's take the velocity versus time relationship because it's the most useful. So this is velocity, and that's time. And it's a constant acceleration, so we're going to get a straight line graph. I don't care about its numbers. I just care it's going to be a straight line. And then I start asking myself mathematically about it. So the first thing I say is, well, that's a straight line, so y equals mx plus b. That's the equation for a straight line. So, well, in this case, y is going to be vf. And m is going to be my acceleration. And my x-axis, well, that's going to be my delta t. That's really delta t there. And where I go through the y-axis intercept is my vi. So all we have here is this is a linear equation for that graph. But it's still just a linear equation. And so then you realize, oh, but look, I've developed a relationship that relates final velocity, initial velocity, acceleration, and time. This time meaning change in time. Yeah, delta t. It's not the time, but it's the time interval, delta t. So that's kind of cool. Rather than the graph, I can just think about the equation. It's to say the same thing. It's just it's Sometimes the equations are more useful and sometimes the graphs are more useful. But I got the equation from the graph, not the other way around. This one is a trapezoid. In Britain we call it trapeziums, like gymnasium, but here we call it trapezoid, yeah? So it's a trapezoid, O-I-D. Trapezoid. And that means it's like a triangle with a bit cut off it. It's basically, the way you get it is, you take the average height, you imagine cutting off this little triangle here, and slipping it into there and making a nice rectangle. And the rectangle is the average height times the width. Again, I'm going to change this every time. That's going to be delta t. So it's the left-hand height plus the right-hand height over 2 times the width. This is the average height times the width. And now we look in terms of what's in our graph, and we go, well, it's a half VI plus VF times t. So I got my second equation. My area under the curve, of course, is my displacement. So my displacement is equal to a half VI plus VF times the time interval, the duration, if you like. Let's do the same thing, but now let's not think of it as a trapezoid. Let's think of it as a rectangle plus a triangle. So I say, well, it's going to be the base times the height plus a half the base times the height. I shouldn't put x's in, should I? I should just put parentheses. It would be a lot clearer. Don't know what I was thinking of when I put these x's in. And so, well, for the base, I have VI is the height and delta t, again, delta t is the width, so that's that guy. That is my rectangle. And then for this triangle, it's a half times this difference in height, which is VF minus VI, times delta t. So there's my expression. Now, that's a correct expression, but it's not so convenient because it's using a lot of the same letters that I used over here. It's correct, but we can make it more useful. We make it more useful by saying, well, look over here. VF minus VI is equal to A delta t. So I have VF minus VI there. So let's replace that by A delta t. And I get delta x equals VI delta t plus 1/2 A delta t squared. Now, that's a more useful expression. I'll explain why it's more useful in a minute, but that's a more useful expression. They're both correct, but that's a more useful expression. And then for the fourth equation, you take VF equals VI plus A delta t, and you take VF squared equals V plus A delta t all squared, and you massage it and manipulate it, and I don't care, this is just, and you end up with your fourth expression. VF squared equals VI squared plus 2A delta x. All coming from these equations, these graphs. Yeah. Why do I like these graphs? Let's list the parameters, the variables that I deal with. I have displacement. I have VI. I have VF. I have delta t, and there's one more. What's the other thing that comes up? Acceleration. 5 parameters. How many? I'm going to get rid of this equation, so yeah, I'm going to get rid of the writing, so yeah, can focus a little bit on that. How many variables are there in this first equation? 4. How many in the second? How many in the third? How many in the fourth? There's 4 in each of them, isn't there? Which one's missing from this first one? Displacement. What's missing from the second one? What's missing from the third one? What's missing from the fourth one? So if I give you a problem, so how does this work? Equations work because one equation means one unknown. So from a point of view of asking questions, I've got to give you 3 out of the 4 things. Yeah. So I've got to give you 3 things, ask you for the 4th. One of them I don't mention and it's irrelevant. If I don't mention displacement, that's the equation you use. If I don't mention acceleration, that's the equation you use. If I don't mention final velocity, that's the equation you use. If I don't mention time interval, that's the equation I use. So I got all my bases covered with these 4 equations. Yeah? You don't need to know how you get them. I want you to see it. You do need to know them. Okay? You do need to know them. Let's say for next quiz, not today's quiz, but the next quiz, those 4 equations will be part of the questions. Let's just say that now, so you learn them. Okay? I'm going to ask you about a calculator issue, but we'll have those 4 equations, and I'll have 2 questions on calculator issues, and I'll be clear about what they are. Learn those 4 equations now. Know them for next. When are the quizzes? Is it next Monday or next Wednesday? Let's look at our calendar. Quizzes come on Mondays. So next Monday, know those 4 equations. Okay? You're right. Oh, the next quiz is after the test. Okay.
Wait, what?
The next quiz is after the test. Learn these 4 equations. Learn these 4 equations for the test, because they're going to be. I know they're going to be on there. You know. Okay. You can do the same thing using calculus. You can say, well, let's look. A is equal to dv by dt, so v equals the integral of a dt, and you just play your games and you go through this bit and you can derive the equations. You know. You can do the same thing. It's 2 pages of it, but you end up with all your equations. Some people prefer this, some people prefer the diagram. I'm amazed by the diagrams that you can get it out. You know, I'm a visual thinker, but I would never have guessed you could have got it from there. And I would not have been able to invent that myself. It's a really smart thing. The first time you see it, you go, whoa, this is really impressive. I go, whoa, this is really impressive. Once you see it, the cat's out of the bag, and you say, can I do that to some other things? But this is, the person who did this, you've got to take your hat off to them. They were really smart. And the person that did this for the first time, it was Newton, I guess, you've got to take your hat off to them, because they were really smart at the same time as well. We just need to know the outcomes. Let's do some. At t equals 2 seconds, the blue sports car is at rest. Let's draw our road. I'm doing one-dimensional stuff since. Here's my sports car. It's t, so t equals 2 seconds. Let's put a clock here, and that's 2 seconds. Blue sports car starts at rest, so my v is 0 meters per second. At t equals 6 seconds, so now my clock at 6 seconds. My blue sports car has a velocity of, whoa, minus 12 meters per second. What's the constant acceleration for this journey? Well, let's get this. This is vi. This is vf. How do I know that? Because the times, yeah? 2 comes before 6, so vi must be 2, and the 6 must be vf. I don't have to start my journey at 0. I mean, it's not 0 on the calendar. It's, you know, whatever it is, 2017 since we put a 0 line. So we often start halfway through a time interval. Who cares? So don't think that it's always going to start at 0. It rarely starts at 0, actually. But you've got to visualize. And then you turn around and say, well, what do I know? Now, later on, when you get really comfortable and you're doing stuff that's a bit more straightforward, you might skip this step, but I would not skip it at the moment. I'm going to go, well, vi is equal to 0 meters per second. I'm going to go, well, vf is equal to minus 12 meters per second. I'm going to go that delta t, which equals t final minus t initial, is equal to 6 minus 2, which equals 4 seconds. And I'm going to go, I want a. So then I look at those and I go, well, what connects these things? And with practice, you can see it. If you don't know initially, write all your 4 equations down, and then you'll spot it. But you have to very quickly get to the stage where you go Vf equals Vi plus A delta T. Now, in math, you might have been told to rearrange your equation before you put numbers in. Were you taught that in algebra? Were you taught to always rearrange your equation to isolate the desired value, then put your numbers in? I'm going to tell you to put your numbers in first. Because there are times, especially when you're working with delta t squared equations, when you can sometimes, what would looks like a quadratic comes down to just a simple thing because something cancels out, because there's a zero in front of it. So put your numbers in, it'll make life a bit easier. So I'm going to say minus 12 is equal to 0 plus A times 4. So 4A is equal to minus 12, so A is equal to minus 12 over 4, which equals minus 3 meters per second squared. Just double check I did that right. Vf is 12, 0, A delta T. Yeah, cool. So there it is. That's what they're like. They're not all as straightforward as that. Sometimes I can make them a bit more complicated, but in principle, that's the approach. My advice as your coach, always do a diagram, always make a list, always write down your equation, put your numbers in, you get the answer. You'll make fewer slips if you always do that. If you do any part of that in your head, you're going to make more slips. So, you make your choice. Negative sign means what? What does a negative sign on the acceleration mean? It's pointing, the acceleration is pointing towards the negative direction. So what does that mean for this journey? If you were to describe this journey to me verbally, blue sports car was moving to the right, was stationary. Yeah? Yeah? It then, oh yeah, it then started accelerating to the left, and at t equals 6 seconds, it had a velocity of minus 12 meters per second squared. Yeah? So, can you spot something that's not correct about my diagram? It doesn't matter. You won't know it's not correct until you get the answer. But can you see something in retrospect that it would have been better if I'd drawn my diagram in a different way? Yeah, actually, it went that way. It went in the opposite direction. Yeah? So really all that happened is it kind of started over here and it went in that direction. And here, you just take those two bits and you swap them around. It does not matter. I'm not saying correct your diagram. I'm just wanting to point out that you can look at the numbers and they affect your diagram. This is exactly how I would do it. I've put my first thing on the left, put my second thing on the right, unless I have a good reason not to, you know. At t equals 3 seconds, a red truck has a velocity of that. Red truck has a constant acceleration of that throughout its journey. What is the velocity of the red truck at 9 seconds? So a red truck, 3 seconds, Vi plus 7 meters per second. Constant acceleration, it's a negative acceleration. So I'm going to put it down here because it's constant. A is equal to minus 2 meters per second squared throughout the journey. What is the velocity of the truck at t equals 9 seconds? Again, I'm just going to put it on the right-hand side. I don't exactly know where it is on my number line. And I want to know my V final. So it's a way of visualizing. I make my list. Vi equals plus 7 meters per second. A is equal to minus 2 meters per second squared. Vf is what I want. Delta t, which equals t final minus t initial, is equal to 9 minus 3, which equals 6 seconds. Come along here. Oh my word, it's the same equation. I've asked for something different, but it's the same equation. You know, there's 4 things in an equation. There's 4 possible things I can ask you. Just got to give you the other things. Vf equals, oh no, it's not the same. Yes, it is. Vf equals Vi plus A delta T. Shove your numbers in. Vf is what I want. Vi is plus 7. A is minus 2. Delta T is 6. Vf is equal to plus 7 plus minus 12, which equals minus 5, I guess, yeah? Meters per second. So Vf is equal to minus 5 meters per second. So there's my answer. So this was traveling to the right at 7 meters per second. And by the time you're at 9 seconds, it's traveling to the left. It's traveling to the left, yeah? That means it's traveling to the left. That means it's traveling to the right. So it's gone down here, and it's turned around and come back. So this is where you're at 3 seconds, and this is where you're at 9 seconds, yeah? I don't know where it is on the number line. I'm just trying to show you those things, yeah? Cool. Red truck has a velocity of plus 15 meters per second when it crosses the start line. So now I've got positions. So here's my red truck. And Vi is equal to plus 15 meters per second. Crosses the start line. As a constant acceleration of minus 3 meters per second, A equals minus 3 meters per second squared. What is the velocity of the red truck when it has a displacement of plus 5? So this is plus 5 meters. This is 0 meters. And I want to know what the velocity is. So this is V final equals, I don't know. Now I do know that the point of interest is to the right of the start point, because I'm actually giving you positions. Vi is equal to plus 15 meters per second. A is equal to minus 3 meters per second squared. Delta x is equal to the x final minus x initial, which equals plus 5 minus 0, which equals plus 5 meters. You can kind of see it's an arrow that goes from here to here. And I need one more thing. Oh, I need to know what I want to find, which is Vf. Okay, so this has a Vi in it, a Vf in it, a delta x in it, and a in it. So let's think. I have Vf equals Vi plus A delta t. That's not good. I have Vf squared equals Vi squared plus 2A delta x. Is that good enough for me? I got Vf, I got Vi, I got 2A's. Yeah, that'll work. Okay, so I go Vf squared is equal to Vi squared plus 2A delta x. And again, you shove your numbers in. So Vf squared is equal to 15 plus 15 squared plus 2 times minus 3 times plus 5. It's not 5, it's plus 5. Yeah? So Vf squared is equal to 150 plus 75 is 225 plus 225 added to 2 threes are 6, 6 fives are 30 minus 30. Vf squared is equal to 100 plus 195. So Vf is equal to the square root of plus 195, which equals, get my handy dandy calculator. Second square root, need my glasses, 195 equals 13.96 meters per second. It's positive 13 point. Now there's an issue. Okay. Most people are going to put down positive 13.96, and that would be acceptable. So let's just talk about this, and I'm going to bring in a subtle point, but a very important point. So basically, what did I do? I drew my diagram. I extracted my list. I found my equation. I used that equation, and I solved. From my perspective, those three problems are all the same. I just changed the variable, I changed the information, but it's the same. This is how you do these problems. You visualize, you make a list, you find an equation, you do your math. And if you get it wrong, you made a specific mistake. You either made a mistake with your diagram, or maybe didn't draw one. You made a mistake with your list. Maybe your diagram was wrong, so your list was wrong. Yeah, made a mistake with your equation. You need to remember your equations, or you made a mistake with your math. But I think when you get a problem wrong, it's important you go through and say, why did I get it wrong? And don't write it off as bad luck or a slip. Okay? If you're making slips, slow down and don't make slips. But diagnose, because it may be that you're consistently drawing your diagrams wrong or not drawing them, and you keep walking off the same cliff all the time. In which case, you know what to do. You've got to fix your diagrams. Don't come in and say, you know, I don't know these equations. You know the equations. It's the diagrams you don't know. Or if your diagram's okay, but you don't know the equations, then work on the equations. You know, it's not just I got it wrong. It's like, why did I get it wrong? And is there a pattern to that so I can fix it? Okay. Now, there's a subtle thing about this, which is the mathematicians will tell me this. No, that's a math answer. So, but you're on the right track. So, square root. What sign does the answer of a square root have? Plus or minus. In math, who cares? We put the absolute value down, yeah? In physics, it really matters because plus 6 meters per second is going to the right and minus 6 meters per second is going to the left. It's not just a sign, it's the way you're going to go for the rest of your life, you know? It's like two choices. Which one are you going to make? Positive or negative? And it really matters. So how can I have an ambiguous answer for this question? How can there be a positive 13.9 meters per second and a negative 13.9 meters per second? Let's see if we can figure that out. So, here's the track, and here's the car. And it's going down here. Now, here's my velocity, and here's my acceleration. Is it speeding up or slowing down? So I'm going to go in this direction. We're going to go slower, 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 slower. I'm going to go there and I'm going to stop, aren't I? And then what happens when I stop? I have zero velocity and a negative acceleration. So what do I start doing next? I turn around, I start going faster, 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 faster. I turn around and go back. And can you see, because I gave you the start position and I gave you the end position, there are two times when you pass that end position. There's one time when you're going to the right, but there's another time when you're going to the left. And when I'm going to the right, I have a positive velocity. And when I'm going to the left, I have a negative velocity. And they are equal and opposite because we're in a frictionless world. So I should have positive or negative. And in this case, the question is ambiguous. It depends, do you mean the first time I crossed this line? Or do you mean the second time I crossed this line? And I didn't make it clear, so most people put down the first time they crossed the line. I'm happy with that. It's like, you know, I'm not trying to catch you out. I want to just point out the subtlety. But there are times when based on the visualization of the problem, when you know it should be a positive or negative answer. If I throw something in the air and I want to know the velocity at this height, if I throw it up in the air, or let's say I'm on a diving board. Well, let's say I'm on a diving board. Let's go, I'm on a diving board. And I jump up in the air and I come down here. You know, down here, it must be a negative velocity because you're going down towards the water. Up here it could be ambiguous because you go up and then you come back down. But when you're below the diving board, you know from the physicality of the situation, it's a negative velocity. The math will not tell you that. The math will say, well, it could be plus 4 meters per second, but it could be minus 4 meters per second because you're going to use a square root to find it. And you have to know that's a negative 4 meters per second because I can only be going downwards at that point. So can you see how it's kind of like there's doing the sums. The math is the least of it. The numbers are not what it's about. It's about the visualization. And as engineers, we need to be able to visualize it. It's a different skill. It requires math, but it is not math. It's a different skill. So avoid that tendency just to, is the number the right number? Start trying to visualize and interpret. And the more you do of it, the better you'll do. I'm going to stop there. We did 40 minutes. I'm going to try and stop there. So I'm going to